Hi, everyone. Good afternoon. Hope you all have had good lunch and would not be sleeping in the session, so hopefully. My name is Deepa Shinde. I'm lead architect in Pharma and LifeSciences in Microsoft UK, and I cover technologies like intelligent applications, AI, machine learning, and quantum computing. That's enough for me. So today, I'm going to talk about Microsoft's vision in quantum computing and what we are up to, basically. Whenever I do these sessions, I do have a quick couple of minutes that talk about difference between classical versus quantum compute. I know Marta has covered that already, so I'm going to take a very little stab at it because it's been covered, and I don't want to bore you with the same content over and over again. So when we look at classical computers, right, why did we build them? We built them to help us to do better arithmetic that we can't do quicker enough. We built them to help us do our workflows. Today, with the advent of AI, and with agents, they can also take some decisions for us, right? So we have come a long way in with classical computers. They actually can research for us, and we have big models and big algorithms that we run with the classical compute. So why quantum compute? There are some problems still classically intractable, right? And these problems are at the root of chemistry, simulations, material science, right? And very specific to the molecular simulation space, basically. Classical computes, even with the supercomputer that we have, best supercomputer we can't. We all drink coffee, we all drink tea. I drink tea every day. So tea and coffee have caffeine. Caffeine is a very small molecule, to be honest. We are unable to simulate caffeine molecule accurately on a classical computer. And it's going to be very difficult to do it with the classical compute. In 1 cup of coffee, there's almost 3 times 10 to the power of 20 caffeine molecules. We can't simulate one properly. Let alone all the water molecules, sugar molecules, everything that's in there, right? Absolutely, we can't simulate that system, basically. But that's a very trivial example. If we look at bigger problems in the world, like nitrogen fixation, it's a process where we actually synthetically create fertilizers. Very, very important process for humankind. It takes about 3 to 4% of world energy to execute this process. And we still have places in the world where food is a problem. Whereas if you look at nature, if you look at plants, they do it quite naturally, right? It's very natural for them to create nitrogenase, which is an enzyme. Why can't we do it? Because we can't get to that subatomic level where these reactions happen, right, with the classical compute. So we know nature operates in a classical manner. And if we have to replicate beautifully what nature has built in terms of systems, us, and everything else around us, then we need to get to the level, subatomic level, that nature operates at. And that's why we need to get at the quantum level. So nature operates at quantum level. That's the reason why we need to study quantum computing. And this is the reason why I'm very passionate about this space, because it's going to solve humanity-level problems for us. So if you look at the quantum, where does quantum happen? Right? It doesn't happen at the macro level. It doesn't happen at 1 millimeter. It doesn't happen even at like human hair level. You have to see right till the end at the nano scale, right? That's where quantum really happens. So we are talking about real subatomic particles here. We're talking about electrons. We're talking about atoms, and even like sometimes lower than that, right? So it happens at a subatomic level. So you can't see it in the daily life. We are quite big for anything quantum, basically. What makes quantum different? Now, there are properties of quantum that makes it different. And these are the properties. There are a couple more, but I'm going to focus more on these. Superposition, interference, entanglement. And why this, right? Now, there's a history behind this, which is deeply rooted into physics. Light performs as both wave and particle. And we knew that in 1800s, right? There was a lot of research done on this. We all know about Max Planck and his quantization theory, right? There was a scientist called as Louis de Broglie. He basically said, why light? Every particle, every matter particle actually behaves as light and particle at the subatomic level. And that's where really quantum mechanics started, basically. That was the real start of it. And we have all, since then, known about double-slit experiments and whatnot that proves quantum. And from there, we know particles actually are wave. They have dual nature. They operate as wave and particle at the same time. And this is where these properties are coming from. So if you think about superposition, it is with the wave-like nature, it gives particle a power to be in multiple states at the same time. So a particle can be in a multiple state at the same time. That's what superposition is. And that's where the quantum parallelism power really comes from, because you can actually harness the superpositions to do quicker processing of information, because it's all about information processing eventually, isn't it? I'm not going to spend time on interference, but entanglement is quite important. And I had a talk before this, which was about quantum communications and post-quantum cryptography. And entanglement is super, super important in that space especially. And with entanglement, what do we know? We know that we can correlate these subatomic particles. And when we correlate them and put them in a state of entanglement, we can send them apart. Not locally apart in the sense in completely like different galaxy for that if we want to, right? If we can eventually. And we can still read the state of another particle. If you can read the one that you have with you, you will instantaneously know what is the state of the other particle. Now, this defies locality that we know, right? So we all have heard about EPR paper, we all have heard about locality, we have all heard about uncertainty principle as well from quantum mechanics. So this actually was proven more than a couple of years ago, and a Nobel Prize was offered to experiment this actually and show that actually quantum is non-local, which means this really, entanglement is real and it really happens. So what is a quantum computer? Quantum computer is basically a machine that uses or harnesses quantum mechanics properties, basically. And who said it? It was Sir Richard Feynman who said in 1981, 82, I don't remember what year it was, but it was 81 or 82. And he said, why can't we harness these properties of quantum mechanics at the subatomic level and actually create a machine which can help us to do better information processing, right? And that's where the race for quantum computing started. Classical world, bit, 0, 1 at a time, deterministic. That's it. It's either 0 or it's 1. And we know how this works, right? It works on the basis of voltages, right? We digitize the signal, and we know with the analog signal, if it is beyond 5 milliseconds or something like that, it's 1. It's below that, it's 0, right? So we have found our way to digitize the signal in 1 or 0, and everything actually operates on this. It's quite highly abstracted now, so we don't get to that level, but that's the level we operate in the classical world. In the quantum world, with the power of superposition, you can see the particle can be in multiple states at the same time. And this goes quite deep, right? It is very difficult to imagine this, because it's not very easy to imagine something like this, right? And there's a lot of mathematics and physics behind this. But for now, if we all just think that the particle can be in multiple states at the same time. So in the classical compute, so what I'm trying to build here is I'm trying to pitch why classical compute versus quantum compute, and why quantum compute is better. So in a classical world, if you have 4 bits, you can actually utilize one of the state at a time. You can read one state at a time from the 16. But if you're with quantum compute, or if you have 4 qubits as opposed to 4 bits, right, then you can actually read all the 16 states at the same time, because our qubits can be in superposition. So what does that mean? That means that 4 bits is equivalent to actually 16 states, if you see here. So 2 to the power of n, to be honest. So this is quite exponential, right? So if you look in the classical world versus quantum world, I'm going to take this quite quickly. So yeah, if you see the scale, right, it's quite exponential. That's where the processing power comes from. So if you think about 50 bits versus 50 qubits, what does that mean? That means immense power, right? At this scale, we can actually start doing things better than the classical compute. And with 300 qubits, it's all the atoms in the world, and all the stars in the world, actually. I'm going to skip this because I know Marta showed this. It's the same thing. So what type of qubits do we have? I mean, see, we are at a phase where there's a lot of research going on in the field, and people are trying to find out various ways of actually creating these qubits and controlling these qubits. So there are multiple different types of physical interpretation of these qubits, and you can create these in multiple ways. There's silicon photonics, there's superconducting, quantum dots, trapped ions, topological, you name it, and you have multiple. There's neutral atom as well. And there are a few more, to be honest. And I'm not going to bore you by going into details of this, but each one of these actually can actually help us to create qubits, and they all have pros and cons, different pros and cons, right? So eventually, in the world, we'll have to get them together to get to a level where we do commercial quantum computing. I'll talk about topological qubit, trapped ion, and neutral atom in some time as well. Now, why? If quantum computers are that amazing, right? Why don't we have them today? The reason we don't have them today is because these are like babies, right? At subatomic level, these particles are newborn babies. They are susceptible to everything that's happening around there. Small frequencies, bit of light, it's gonna put them in an erroneous state, basically. So, and what do I mean by that? By that, what I mean is they are inconsistent. So if they give you an answer as 0, 1, once, the other time it might give you an answer as 1, right? So what do we need for better computation and accurate computations? We need consistency. We need reliability. We can't get those from the physical qubits because they are error-prone, highly error-prone. And that's the NISQ era, basically, and that's what we are in today, basically. If you think about quantum computer, I know this was discussed as well. Now, because these are so erroneous, we have to keep them in vacuum. We have to keep them at very low temperatures, lower than the outer space. And that's why you see this chandelier, right? This chandelier, a chip is very small, but you have this cryogenic device and a lot of other things to kind of maintain that vacuum and the coldness, basically. There are multiple algorithms, like in classical compute. There are multiple different algorithms that have come to play. Some of these are quite important because if you Deutsch-Joja is actually not necessarily of practical use, but it proves quantum computing. It's an algorithm that kind of shows reading a constant versus a variable, and how with quantum computers or qubit, you can actually do it in 1 qubit versus classical takes 2 bits, right? Grover's search actually is an algorithm that tells us that we can actually search better than the classical world using quantum computers. Quadratic speed up, to be honest. Generally, in the classical world, you would at least take the complexity is n by 2 at least. But with the quantum world, it is in square root of n, right? And it is a risk to symmetric algorithms, actually, because you can find the key, search the key using this algorithm, but it's going to take us years and years to get there. With Shaw's algorithm is actually the real threat to the asymmetric algorithms that we have, cryptographic algorithms like RSA, right? And there was a talk on this, so I'm not going to talk a lot about it. It just factorizes it's better at factorization, super polynomial speedup, basically. Variational quantum algorithms like VQE are very important for hybrid quantum computing. When quantum computers come to play, soon, hopefully, we are not going to run entire routine on quantum. And the reason for that, it is going to be a scarce and expensive resource, but it is not good at doing everything. It is good at doing small data, super polynomial problems, right? We don't want quantum computers to do arithmetic. Waste of them, and they would take longer time as well, right? So we don't want them to do everything. So we need to build hybrid systems. And that's what these algorithms help us to do. So I'm going to very quickly talk about hype versus clarity, right? When we kind of started doing quantum computing, it was said that we can do everything with quantum computers. Like I said before, we don't want to do everything with quantum computers. And why? Because there are problems in the world, for example, like molecular simulations, right? In molecular dynamics, what happens is when you have multiple atoms or multiple electrons, actually, interacting, when the entanglement, because electrons naturally at that subatomic level are going to get entangled. That's their nature, that's what they are here to do. If that entangled active space, it is called as basically, if that active space goes beyond, for example, 20 entanglements, that's when you need quantum computers to come in, because classically, we can't simulate anything beyond that. And why do we want to simulate anything beyond that is because we need accuracy. For example, for drug discovery, right? We need accuracy in that process. Why does drug discovery takes longer time? Because if we have too many candidates going into the wet lab, it means longer cycle, longer R&D cycle. We need to take absolutely accurate materials into the wet lab so that cycle reduces. And accuracy is what quantum computers bring actually to the table as opposed to anything else. So for us, it's the accuracy. And you can see here very quickly. Classical kind of goes exponential, and quantum computing kind of goes linear, right? And you see the crossover time as well. But even with that crossover time, we don't want to do everything around that crossover time, to be honest, because there are multiple different ways, classically as well, that you can optimize some of these processes, like using AI or using machine learning, right? So we don't want to do things which we can do quite nicely today with quantum computers, basically. So at Microsoft, we believe that these are the areas which are majorly materials, chemistry, R&D, drug discovery, is what are going to be the first applications of quantum computers. And that's what the compute should be used for as well, because when you make a difference in the material space, we touch most of the humanity, basically. So look at iron age, look at copper age, semiconductor age. We have been able to actually make a difference for entire human race. And that's what we want to do. We want to pick up a problem that is real and can be targeted truly with the quantum computer. So it's a small data and super polynomial problem. And why small data? Because quantum computers, if you look at two chips, right, they are not very good at taking too much of data, to be honest. So you need to keep your data low. And I'll talk about this in further slides as well, like how you can use quantum accurate data to actually feed your AI models. So what is our strategy at Microsoft? So there are 5 pillars in our strategy and our vision. The very first one is building quantum computer, which is the hardware. Second is building a platform where we can do hybrid workflows. So bring quantum, bring HPC, bring AI, and run your workflows. And the third one is basically building the quantum applications, because we know certain spaces quite well where quantum is going to be the first target, and we can actually abstract away a lot of lower level things from the researchers, for that matter. They don't need to know when to run quantum computer, when to not. We can take care of that. So that's the third pillar. The fourth pillar is quantum-safe cryptography, basically. So quantum-safe is a program to do post-quantum cryptography, and we're highly invested into it. One of the most accelerated vertical, actually, in our quantum program, which is making sure everybody's safe, and we ourselves should be safe as well. Quantum Ready comes from our work with UN, actually. So we have been nominated as a partner for the 100th year of quantum technology and science. This is that year, basically. And as per that, we are actually creating a lot of readiness program for entire world to learn about quantum and get ready for the quantum. That was the strategy. Coming back to the physical and logical qubits, there's nothing like good physical qubits, right? They're theoretical. They don't exist. There's a lot of noise, and the real physical qubit actually looks like that, very messy, right? What are logical qubits? Logical qubits are nothing very similar to our classical world, right? They are error-encoded qubits. And what they do is, basically, you have error qubits and you have data qubits, and they help you to kind of learn the error while you are actually computing as well. So logical qubits are actually error-corrected qubits. And you can relate that back to the classical world as well. So level 1 is where we are today, which is NISQ level, which is noisy quantum computers. How much can we do with them? Not a lot, and that's why you don't see a lot of practical applications, because there's a limit to what you can actually do with the NISQ-prone quantum computers. We at Microsoft truly believe in logical compute, basically, logical qubits. And that's the level 2, and that's what we are striving towards. And we believe when we hit 50 logical qubits, we will be able to actually go beyond classical compute. And where are we today? We are at 28 logical qubits, 24, 28 logical qubits, actually. They are going to be better than NISQ, and there are going to be certain applications that they will actually implement better than the classical compute. Level 3 is the industrial level, which is 1,000+ logical qubits, basically. And we need a lot of physical qubits to get that. So let's hold on with that, and we'll talk about it. I'm going to skip this slide because I'm running out of time. So I'm going to quickly, oh yeah, this one, right. So with the So what do we see with the logical qubits, right? So this is one of the experiments that we did with our logical qubits, and we saw that the true ground state of a molecule, right, is closer, is far more accurate than the logical qubit than the physical qubit. I'm not going to go into details of this. This was based on the chirality of the molecules, basically, and I'm going to skip that because there's a lot of other details in it. So I'm going to play this video and see if the sound comes through, but it shows you what logical qubits are. I skipped some part of the video, but that's OK. So that's where we are. Last year was very good for us. We started off with 4 logical qubits with Continuum, the trapped ion technology I talked about. 12 logical qubit quite quickly. I remember I was at IEEE Quantum Week that time when we had this announcement with 12 logical qubits, right? And I was very impressed and emotional at the same time, because it was brilliant to come up with this so quickly, basically. And when we had this, the beauty of this was we didn't use the same amount of physical qubits. It was far less. We tripled the logical qubits, but the physical qubits were less than half of the physical qubits that we used the first time. 24 logical qubits is what we could achieve with neutral atom hardware with atom computing. So we are working with different providers. You can see what we are doing here, right? We're trying to work with multiple providers, because even today, we don't definitely know which is the best compute, right? And we want to accelerate the space. We want to accelerate the community. So we are working with multiple different providers to find the best path. And what we have done here is, when we say logical qubit, there is an error correction virtualization framework that needs to be built on top of the hardware. And that's why you get these, that's how you get these logical qubits. And these are high fidelity, very reliable. When I say that, what do I mean? I mean that they are consistent in terms of the results that they give, right? So reliable quantum operations per second. And we have proven that. And there are multiple papers you can read about it. So we are at 24. And if you are at 2024, hopefully we will get to 50 very quickly, which is when we will be able to solve problems better than the classical compute. That's what our hope is. And early 2026, we are hoping to release this compute for the customers. Now, when we look at this, if you see, if we need to get at 100, which is where the level 2 finishes, we need 10K physical qubits. With atom computing, which is a neutral atom technology, they are about somewhere around 1,000 plus. To actually create physical qubits as well, it is not easy. So to get to the commercial advantage, 1,000 plus logical qubits, we need 100K physical qubits. That's going to be very difficult to do. And that's why we believe in our first-party hardware, which is topological qubit. You must have heard about Majorana, one chip, which we launched recently. That chip is about a topological qubit. And why is that? What's the difference? Like, why is that qubit better than anybody else? Because it is small, fast, controllable. And what do I mean by that? What I mean by that is it is small, first of all. When you saw the chip, we have like 1 qubit is 1/100th of millimeter, right? Very, very small. It's controllable, digitally controllable. So we can control through digital signals. Most of the other hardwares are analog controls, right? We'll come to fast afterwards. So if you look at this qubit, right, it is built using Majorana fermions. Now, Majorana fermions are basically quasi-particles. There's a lot of physics behind it, so I'm going to skip the physics. But what it means is this qubit, the way it is built, it actually has some error correction intrinsically. We braid multiple particles to create 1 qubit. And if this qubit has intrinsic error correction, definitely we don't need 100,000 physical qubits to get to the industrial scale. And that's what we believe as Microsoft. And that's why we're researching in it for 20 years. Majorana fermions, or topological qubit, that state itself was theoretical until 2023. Our researchers could actually produce the state, but then control it. And then now we have hardware encoded it, which means we have put it on the hardware on the chip. So there are 8 on this chip. We want to get to million or more and put some error correction on top of it so that we can get to the industrial scale, basically. So that's more or less I can cover about Majorana, because otherwise it's far more physics heavier, and I'll skip that in the interest of time. This is the compute I was talking about, hybrid compute. So the AI engine, the quantum engine, and the HPC engine working together in tandem. Now, what's the beauty of this is, like I said before, we don't want quantum to do everything. We want to pass the quantum routine to quantum compute only when it is needed, right? The other thing that we are looking at is when you look at this, this is Azure Quantum, basically. With Azure Quantum, there are multiple different hardwares that are provided. What we are trying to do is we're trying to help you to run your algorithms on whichever hardware that you want. So we have neutral atom, trapped ion, topological, hopefully will come soon. Our logical qubits will also come in 2026, right? So on this platform, you can bring your any software language. Q# is ours, but you can bring Qiskit, which is very, very popular, from IBM. You can bring Cirq from Google. Write your algorithms. We write the interpretation layer. We have already written the interpretation layer. So different hardwares need different interpretation. And we have done that job for you. So that's what we do with our compute, basically. And of course, you can see the qubit virtualization system as well, right? That's where the error correction sits. I'm going to skip that. There are multiple partners we are working with. I think I've already explained this, like why materials and chemistry, because it impacts everybody's life, basically. And that's what Satya told us. Compress 250 years of chemistry into 25 years. And that's what we all are behind. That's the motto. So AI will bring the speed, HPC will bring the scale, and quantum will bring the accuracy to these processes, basically. So this trio will actually help us run these algorithms and run the quantum applications, basically. And the application that we are creating for our customers in materials, chemistry, and R&D space is called as Azure Quantum Elements. Hopefully, this will grow further for other industries as well. But today, it is for these industries. I don't have much time, so I'm going to skip. I think I mentioned this already, right? Reducing the wet lab time. That's what we are doing with Azure Quantum Elements. Protein folding is another problem that we are working on using Azure Quantum Elements. Of course, in tandem with AI. It has to be along with AI. This is a new material that we actually created using Azure Quantum Elements with Pacific Northwest National Lab from US. We could create a new battery material in 6 months instead of decades. Actually, it takes years and years to create a new material, new battery material. And the battery that you see there is actually real. And we have a clock that is fueling through that. And this whole process used AI and HPC and quantum simulation, actually, not the quantum compute, because we still are yet to get the quantum logical compute. But all that process actually helped us to reduce the time. So what I'm trying to say here is it's going to be hybrid play with AI and with compute like HPC. I've spoken a lot about responsibility and reliability actually in the other sessions. So I'll encourage you to go through it. It is majorly about our quantum safe program, which is we have to start now because there's a threat around harvesting data and decrypting it afterwards. So if you're sitting on a data which needs to be secure for a longer time, and the quantum computers would be probably available before that. So then you have to start working. You have to start working now. So there's a Moscow's theorem which you can go and look for. Actually, it's in my other presentation as well. It helps you to understand how much risk you're sitting on as an organization. So we are very actively working with NIST and with other players to actually implement post-quantum cryptography algorithms in our systems, because we really are service providers and we're sitting on a lot of your data, so we have to make sure it is safe. So we are working on it for like a good 6-7 years now, have worked along with NIST and other governments to make sure the new quantum resistant algorithms is what they are called as, are actually there, and we are actually implementing them in our systems as well. And this is how we are helping our customers basically to kind of look at post-quantum cryptography and look at their estate, assess it, and look at how they can solve their problem and how long it's going to take them to move over to the new algorithms, basically. So that's actually all of it. I ran over, I think, by a couple of minutes, and sorry for that. But yeah, I mean, if you have any questions, please feel free to ask. Yeah, go for it, please. Yeah.
The material you just mentioned, the new element you created.
I don't know the name of the material, to be honest, but it is. So the gentleman is asking, what is the name? What is the new battery material that we created? It's a new molecule which I don't know exactly what it is called as, but of course it has lithium, but less lithium and more of other material. So what happened was, if I go back to that slide, I can quickly explain to you. If you're interested, then I can quickly tell you what happened at every layer. But unfortunately, I don't know the name of the material. So if you look at this, right, so we started off with screening 32, I don't even know how to pronounce that. So there are many millions, 30 millions of these different combinations that we actually observed using AI model. And what this AI model did was, it looked at different properties of these materials, which are apt for the battery type of material. So we kind of reduced down from these many candidates to lower candidates, which is 5,000. And I don't know how much you know about chemistry, but there are various different techniques like DFT, grounded into molecular chemistry, basically. And we applied some of the like accelerated chemistry, accelerated DFT are the services that we have, which are rooted into AI and HPC. We applied it on top of that, so it went to 800. And from there, we actually used human validation to get it down to 18. So instead of taking hundreds of target into the wet lab, we took 18. And they built all 18 and realized only one out of them, that was actually the one that is giving good battery, sustainable battery, basically. But that was the process. Unfortunately, I don't know what the name of the material was, but good question. I'll find it out. Thank you. Yeah, sure.
Design better batteries, clean water, design drugs, new materials, 250 years and 25 years. I think the vision is to increase the chemistry development. But in the end, what I think is that you are reaching the biology level. So it's not about chemistry, but biology. So I think we are touching the nature, right? Because the traditional computing couldn't help us to touch the nature. But seems like 25 years is not too solve the chemical problems, but biological problems, don't you think so?
Yeah, so we are. So we are researching into small molecules, which is majorly chemistry, but also large molecules, which is biological in nature. So with pharma companies, right, we are working on the large molecules as well. I cannot say that we have been able to crack it today. We are trying to look at it, not just with quantum, but actually with AI as well. So you are right. It is not just materials and chemistry, but it is also in tandem with biological processes. So it will. We are already working on that. Yeah, absolutely. Any more questions? I think we are good. OK, yeah, one more. Please, yeah. Please feel free to leave if anybody wants to leave. I can carry on, yeah. Can you be a bit louder? I can't hear you. Mm-hmm. Yes, we do. Yeah, physical. Yeah. So day before yesterday, Marta was also there, actually. We were at Economist Quantum Impact event, actually, in London. And we had the entire chip along with the chandelier there. I mean, not the real chandelier, but the chip was real. So the chip is real. We have 8 qubits on it. And the beauty of that is we have been able to get the connectivity between the 8 qubits, which is very difficult, to be honest. So we have 8 qubits on it. And like I said, the intention is to get more. So the way that works is, if you're interested, then it's a combination of superconductor. So certain materials at very low temperatures can show superconductivity. So we are using aluminum to do that, basically. So we put it at a very low temperature. On top of that, there are nanocables. And these are semiconductors. So these nanocables are very small. They are like, you can't see those with the naked eyes. They are very, very small, like 100 of the sand particle, to be honest. We layer it on top of it. And what we do is we send a high voltage. So the combination of low voltage and magnetic field, basically, magnetic field, voltage, and the low temperature actually puts it into a state which is called a topoconductor. Now, topoconductor is a different state of matter. It's neither solid, nor liquid, nor gas. It's a different state. And in that state, you actually can create these Majorana fermions, which are quasi-particles. When I say quasi, they're half electrons. They're not full electrons. And you put them, you braid them on the two sides of this wire, or this thing that you have built, and you put other particles in between, and that basically creates your one topological qubit. And we have been able to control it using digital signals, basically. So that's how it is built. And it's real. All those 8 qubits are real. But it still needs to be, like I said, in the process, it still needs to be at very, very low temperature, lower than the outer space. So you still need the chandelier. And the chip is so small, but you have the big unit on top of it. Yeah. Sure. See, I'll tell you, we don't have a roadmap, and Microsoft generally doesn't do that. I think the very first time we have told that we will come out with something in 2026 with logical qubits, not with topological qubits. We have done that the first time in the whole quantum work that we are doing, because we're kind of sure that we will get there. With topological, it's very difficult. It was in 1939 that Majorana actually suggested this particle, theoretically. It wasn't created until 2023. But after 2023, we could create it, we could control it, we could put it on hardware. But we now need to get it beyond that, right? So the progress has been quicker, but we cannot give you a timeline because it's not easy. We don't know. It kind of underpins the research, defies physics, which sometimes you don't have much control on. So there's no roadmap, to be honest. Yeah, we know what we want to do, but we don't know when. Yeah. Sure, Norris, yeah. Any more questions? Sounds good. Thank you, everyone.